All right, so let's talk a little bit about working with solutions. Since the majority of chemical reactions happen in an aqueous solution, a lot of times we have liquids that we want to mix together to react. So it's convenient to know what volume we need to add to another volume to make it happen. And so we're going to be talking about concentrations and volumes. We know that the behavior of solutions often depends not only on the nature of the solute, but also on the concentration. First, let's talk about what is a solution. I think we mentioned this earlier, but we always dissolve one substance in another substance. So it's usually a solid dissolved in a liquid, or a liquid in a liquid. But the thing that we're dissolving is the solute, and the liquid that we're dissolving in is called the solvent, and together they make a solution. So you can see below, if we're trying to make a salt solution, then water is the solvent, salt is the solute, and together we have the solution. Now, you kind of already know what concentration is. The concentration, well, in general terms, how strong is that? How weak is that? That coffee is really strong, etc. So it refers to how much solute is in a certain amount of solution. We're going to do it much more quantitatively, however. Okay, so the unit for working with chemistry especially is molarity, molar concentration. We use the capital M as the unit. Molarity stands for, it's defined as the number of moles of solute divided by the liters of solution. So let's look at a simple example. So let's say we have 0.0341 moles of iron chloride, and we dissolve it into 25 milliliters. How would we calculate the molarity of the solution? So again, the molarity should be moles per liter. Well, we know the moles. So the moles are 0.0341 moles. And then we just want to divide that by the liters. Well, we're given milliliters, so we need to first convert 25 milliliters to liters. So you divide by 1,000, so it's 0.025 liters. So the molarity then is 0.0341 moles divided by 0.0250 liters, and we get a concentration of 1.36 molar, or 1.36 moles per liter. You can use it either way. All right, what's the molarity of a solution if you have 5 grams of fructose and you put it in enough water to make 100 milliliters of solution? Well, this time, again, we need moles per liter. We have neither of those. So if we take our solute, 5 grams of fructose, and we convert it to moles, grams to moles, we know how to do that. 5 grams of fructose divided by the molecular weight, 180 grams per mole, gives us 0.0278 moles of fructose. And then we already know how to convert 100 milliliters to liters. You just divide by 1,000. And then we can plug it into the molarity formula. And so we have 0.0278 moles divided by 0.1 liter gives us a concentration of 0.278 moles per liter, or 0.278 molarity. Now, molarity can be used as a conversion factor. It's a way of converting between moles and volume. So if you know moles and you want to know volume, you can use the molarity as the conversion factor, because molarity tells us moles per 1 liter, well, you'll be able to convert it. So, for example, how many grams of cobalt chloride dihydrate are needed to make 500 milliliters of a 0.121 molar solution? All right, so if we convert, we make sure that it's 500 milliliters, or 0.5 liters. And now we use our conversion factor, 0.121 moles per 1 liter. We'll get 0.0605 moles of cobalt chloride dihydrate. It's actually cobalt 2 chloride dihydrate. Okay, so now we know how many moles that is. You could also do this as a ratio. If you say, well, if there's 0.121 moles per 1 liter, how many moles will there be per 0.5 liter? You can set those two equal to each other and cross multiply, and you would get the same result. Now, if we take that 0.0605 moles, multiplied by the molecular weight, and I throw this example in there because if you do see a hydrate like this, you do have to add the weight of the waters to the total molecular weight. So you're going to add together the weight of cobalt plus 2 chlorides plus 2 water molecules. And so the total weight is 165.9 grams. Okay, so if you multiply that, you get 10 grams of cobalt chloride dihydrate. So what we have to do is put 10 grams of that cobalt 2 chloride dihydrate and add water up to 0.5 liters, and we'll have our solution. It will be 0.121 molar. So here I have a little picture of the process. So if you figure out how much you need to weigh, you weigh that out on some kind of a scale. 10 grams, put it into your container, and there's containers of very different sizes. In this case, we want 500 milliliters or 0.5 liters. And so we put the powder, the solid in there. We add water, swirl it up a little bit till you get everything dissolved, and then add water up to the mark. All of these volumetric flasks have a particular mark that is the exact volume that you need. All right, let's look at one more example. How many milliliters of a 0.5 molar solution contains 5.40 grams of sodium sulfate? Okay, well, let's see what we have here. Where we know our concentration, 0.5 moles per 1 liter. We're trying to find liters, so since we know moles per liter, and we can find the volume with our conversion factor, 0.5 moles equal 1 liter. But before we do that, we're going to have to take our grams of Na2SO4 and convert it to moles. So that's the first thing we did. 5.4 grams divided by the molecular weight of Na2SO4 means that we need 0.0380 moles of Na2SO4. Or that's how much we want. We want to know what volume will contain 0.0380 moles of Na2SO4. So now if we use our conversion factor, we know that there's 0.5 moles for every 1 liter. So if we divide by 0.5 moles per 1 liter, the moles will cancel. The liters will be on top, so we end up with 0.0760 liters, or 76 milliliters. Again, we could do a ratio if you want to know, okay, 1 liter equals 0.5 moles, so how many liters equal 0.0380 moles, and you could set those equal to each other and cross multiply, sort of like a proportion, and that's basically what we're doing here. But this way, if it's probably very helpful for you to learn how to line up your units. Once you know something and you know what you're looking for, if you put that on top and what you're trying to get rid of on the bottom, you won't go wrong. So using your units is a very helpful technique to use. Oh, there we go. So 76 milliliters of the 0.5 molar solution will contain 5.4 grams of Na2SO4. Okay, as you probably, if you think about it in your just everyday life, if you take something that's concentrated and you increase the volume by adding water to it, what's going to happen to the concentration? Well, it's going to dilute down. So the same thing is true. Of course, molarity is just a type of concentration, and so molarity and volume are inversely proportional. If you add water to a concentrated solution, it will become less concentrated. So we can use this relationship. Mi times Vi equals Mf times Vf, where I's mean initial and F means final. So your initial solution, molarity times volume equals the molarity times volume of your final solution. If you think about it, moles equal molarity times volume. So really, the amount of stuff that we have in that container hasn't changed at all. If you concentrated, and then if you dilute it down, all you're doing is adding water. So the amount of stuff hasn't changed. The number of moles hasn't changed. And so that's why we're able to make these two things equal to each other. But now it's a very handy equation because we can use it to do dilutions. Again, as we add water, by increasing the final volume, the final molarity will decrease. So here's kind of a little bit of a look at what we're going to be doing. If you take a stock solution or a concentrated solution and you measure out a particular amount of it, so that's a picture of a volumetric pipette, and we suck up a certain amount. That pipette has a very particular amount, say 10 milliliters or whatever. Then we put it in our second bottle. So we're taking our small volume of our concentrated solution, so that's MiVi, and then we're putting it into another container, and then we're adding water to the mark, which gives us our final volume and our final concentration, which is more dilute. And so actually here they're using the same equation. This time they're using S's, where they're just talking about I don't know, Vs of solution 1, diluted and saturated or something. I don't know what they're using. I use either I's and F's or 1's and 2's, but you get the idea. As long as you put the correct volume and concentration on the same side, you're good to go with these kind of equations. So let's do a few examples. All right, how many milliliters of a 3 molar H2O solution, H2SO4 solution, are needed to make 450 milliliters of a 0.1 molar solution? So when you do work these problems, a couple of things to note. You want to make sure and get the correct volume and the correct concentration on the same side. So you may not look at that and say, gosh, what's my initial, what's my final? I'm not sure. As long as you get the two that go together on one side, you're going to be fine with these problems. So the key word to look for is of. So you can see here we want to make 450 milliliters of a 0.1 molar solution. So those are actually, in this case, happen to be our final volume and our final concentration. But as long as you put them on one side of the equation, you're good. And so we want to know how much of a 3 molar solution, so those two should go on the same side of the equation. So we identify here the initial concentration is 3 molar, and our final concentration is 0.10 molar, and we want a final volume of 450 milliliters, which is the same as 0.450 liters. And what we're looking for then is our initial volume, VI. How much of the concentrated solution do we need to dilute down to make 450 milliliters of our less concentrated solution? So you could either plug these numbers in now, or you could rearrange the equation to solve for VI, because that's what we're looking for. And so then we can plug our numbers in. So the final concentration is 0.1 molar times 0.45 liters divided by 3 molar gives us 0.015 liters, which is the same as 15 milliliters. And I will say one thing about this equation. Now, when you're doing molarity, it always has to be in liters, moles per liter. When you're using this equation, since molarity shows up on both sides and volume shows up on both sides, it's not critical that you put everything into liters, just as long as you have the same units on both sides. So if you chose to, you could put the 450 milliliters in the numerator, and then when you got the answer, you would get 15 milliliters. So you don't have to go through the extra step of converting, as long as you use the same units on both sides. So what would we need to do here? We would need to take 15 milliliters of the concentrated solution and then add water up to 450 milliliters. If you wanted to even go a step further, you could subtract. Since you're starting with 15 milliliters, you would have to add 435 milliliters of water, and it would dilute down to 0.1 molar. The molarities cancel out, and so our units are liters, and then you can convert that to milliliter. All right, if 10 milliliters of a 10 molar stock solution of NaOH is diluted to 250 milliliters, what will the new concentration be? So again, the key word you want to look for is of. 10 milliliters of a 10 molar stock solution will go on one side. That's our initial concentration and our initial volume, and our final volume is 250 milliliters. So now this time we're looking for our final concentration. All right, there's our equation. There's our initial volume, our initial concentration, our final volume, and our final concentration is what we're looking for. So if we rearrange and solve for m sub f, we get 0.4 molar. Okay, so I hope these equations they're pretty straightforward. So I hope the main thing is to make sure your units are the same on both sides, and that they are that you put the correct volume and concentration on the same side. Okay, so quantitative analysis, as you might imagine, quantitative is a way of figuring out how much of something you have. Analytical chemistry is the branch of chemistry that deals with the identification or composition of different materials, and then specifically quantitative analysis is determining the amount of a substance present. So gravimetric analysis is one subset of quantitative analysis, and it's a type of quantitative analysis where the amount of material is formed, that something is captured usually by some kind of solid. So you take what you're looking for, you convert it to a species that can be isolated and weighed. So it doesn't always have to be a solid, but usually that's the easiest way. So something is converted into a species like a solid, a precipitate, and then that product can be isolated and weighed, and so you're able to figure out an amount. So here precipitation reactions, like I said, are often used. And then these precipitates are usually, so we did a lab with cobalt phosphate where we actually figured out the limiting reagent by filtering and testing the liquid. But if we wanted to, we could have collected that solid that we were filtering, dry it out, and then weigh it, and we could have figured out how much product we had prepared. That might have been another thing to do during that lab. All right, so let's do just a real simple gravimetric analysis problem. What if we wanted to find out how much lead was in a particular sample of drinking water? Well, if you take that drinking water and add some sodium sulfate is soluble because it has sodium in it, but then the sulfate will precipitate out all the lead. And so it will take all the lead out of solution and make it into a solid. So here's the equation of what would happen. The lead sulfate would precipitate. So if we collect it and filter it, and then we dry it and weigh it, we can figure out how much lead there is. So let's suppose we have a liter of sample and we analyzed it by adding an excess amount of sodium sulfate. So we put a lot of sodium sulfate in and captured all the precipitate. So we made sure that all the lead was precipitated. And then the precipitate was isolated and dried and weighed, and it turned out to be 229.8 milligrams of lead sulfate. So what is the mass of the lead in a liter of the water? Well, we have to be a little careful because you realize that lead sulfate is the mass is both lead and sulfate, and so we have to figure out how much of that is actually lead. And they want us to express the answer in terms of milligrams per liter of solution. All right, so again, remember that what we isolated was the lead sulfate. So if we figure out what mass percent the lead is out of the lead 2 sulfate, we can figure out, or sort of, the percentage. What's the mass percentage of the lead out of the total? And then we'll know what percentage of the solid is our actual lead. So the molecular weight of lead is 207.2 grams per mole, and the lead sulfate 303.3 grams per mole, so most of it is the lead, but it's about 68.32% of the solid will be just lead. So now if we take the amount that was given in the problem and multiply it by just the percent of lead, we'll figure out how much of it is just lead. So the amount of PbSO4 was 229.8 milligrams. If we multiply that by 0.6832 or 68% divided by 100, we find out that out of the 229.8, 157.0 milligrams is lead. Now we just need to divide by the number of liters. Since it was 1 liter, it's just 157 milligrams per liter. If we had used a smaller volume, we would just divide by how many liters we actually collected as our final dividing point. Okay, a volumetric analysis is another method used by determining how much of a substance there is based on measuring volumes. Titrations is a procedure that we use in volumetric analysis. So the way that a titration works is that you start out, well, there's kind of different ways, but you you carefully measure the volume of one solution. Now it could be that you know the exact concentration of that solution, or it could be that it's your unknown, but you measure an exact amount of it, so you can see that in picture A. Then you're going to put your second solution that you're reacting with the first solution into your burette, and a burette is just a long skinny tube that has measurements, sort of like a volumetric cylinder. You can measure the volume that you add. You're going to add the second solution into the original solution, and usually a lot of acid-base reactions happen this way, and so there's generally a change in color when the reaction is completed, and so you add the second solution into the first one until a color change happens. That point is called your end point. So it's there's a color change, and so you know the reaction has finished. And so if you know the concentration of the volume, and so you knew the concentration of what you added, and you know now how much you added because you can measure it, then you're able to calculate the moles of substance that you added, and you can relate that back to the moles of the substance that you started with. And again, you know your exact amount that you started with, so you're able to do a calculation. So let's look at an example of that. Okay, so before we do an example, I just wanted to point out something. All right, so let's look at an example, a reaction of sulfuric acid, H2SO4, with sodium hydroxide, NaOH. Here's the reaction, and notice that the balanced equation shows that we need 2 moles of NaOH to 1 mole of H2SO4, so that's important, the mole-to-mole ratio. Suppose we have 35 milliliters of a 0.175 molar H2O4 solution. How many milliliters of a 0.250 molar NaOH solution must be added to completely react with the sulfuric acid? Okay, so we know the moles. We don't know the moles, we know the molarity, moles per liter, and we know the volume. So we know that if we multiply molarity times volume, we'll get moles of H2SO4. Then, knowing our mole-to-mole ratio, we can convert from moles of H2SO4 to moles of NaOH. And then, because we know the concentration of NaOH, we can convert to volume of NaOH. So let's see how that works. So we're going to convert 35 milliliters to liters, 0.0350 liters. And then we're going to, and there it is, we're going to convert that to moles by multiplying by the volume. So 0.035 liters times 0.175 moles per liter. The liters will cancel, and we'll end up with moles if we did that calculation. Then what we have to do is convert from moles of NaOH, convert from moles of H2SO4 to moles of NaOH using the balanced chemical equation. So we know that we're going to need 2 moles of NaOH for every 1 mole of H2SO4. So now moles of H2SO4 will cancel. And then finally, we can convert to liters of NaOH by using our molarity of NaOH. So 0.250 moles per liter. So if we multiply all the way across on the top and divide by everything on the bottom, all of our units will cancel. Moles of H2SO4 will cancel, liters of H2SO4, moles of NaOH, and we'll finally end up with 0.049 liters of NaOH, or 49 milliliters. The key to this is that you have to know that middle mole to mole ratio step, but that's just like we did in chapter 3. All right, let's look at we're going to look at one more example. This one's a little bit more complicated, but not really. So a sample of iron ore is dissolved in acid, and the iron is converted to iron 2+. Okay, now we're going to titrate this iron with MnO4 negative permanganate solution. And this time they're telling you how much you used at the end point, but what we don't know is the concentration. All right, so here's the balanced chemical equation, and the main thing that you need to get out of this equation, is that you have to use 1 MnO4 for every 5 Fe2+ in order to convert it. So the first thing we're going to do, they're asking how many moles of MnO4 negative were needed to titrate the iron solution. Well, we knew that we used 47.2 milliliters, and the concentration is 0.0224 molar. So if we multiply those, first convert milliliters to liters and then multiply, we get 0.001057 moles of MnO4 negative were used. All right, so how many moles of iron actually were titrated by this amount of MnO4? Well, we have to multiply by 5, because 1 MnO4 negative titrated 5 Fe2+. So there were 5 times as many Fe2+, so 0.005286 moles of Fe2+. So how many grams of iron were there? Well, now you just have to take that and multiply by the molecular weight of iron, and you get 0.295 grams of iron. So again, you can figure out the volume of you can figure out the moles by multiplying molarity times volume in liters, and then you can find the moles of the other substance you're interested in by using the mole to mole ratio. And then in this case, so actually we started with liters converted to moles, then we converted to moles of iron using our mole to mole ratio, but we actually this time needed grams, and so using the molecular weight we converted from moles to grams. So if you look back at that sheet, we actually started with liters and ended up with grams. You can do any of those things as long as you know the relationships. All right, so just a little bit of a summary. There are 3 major types of reactions. Precipitation reaction, which is the switching and coming together of ions that form a solid, which is not soluble. Then there were our acid-base reactions, which is also a switching of ions. It's generally a switching of an H+ ion from an acid to a base. Often water is a product, but not always. And then the third one was oxidation reduction, which is the transfer of an electron from one species, the thing being oxidized, to another, the one being reduced. There were 4 types of mechanisms for the reactions: combination, decomposition, displacement, both single and double, and then combustion reactions. And then molarity is defined as the number of moles of solute per liter of solution. Quantitative analysis is the determination of an amount of something in a material. Gravimetric analysis happens when you determine the amount of a species by converting it to a product you can isolate and weigh. Volumetric analysis is when you titrate with one liquid with another liquid. All right, so by the end of this chapter, you should be able to use the solubility rules to determine if a compound is soluble, write any soluble compound in terms of its dissociated ions, predict if a solid will form in a precipitation reaction by using solubility rules, write the molecular, complete ionic, and net ionic equations of any equation that's given to you. classify acids and bases as weak or strong, be able to write the molecular complete and net ionic equation for any kind of neutralization reaction, assign oxidation numbers, balance simple oxidation reduction reactions, calculate molarity from moles or from mass and volume. So you'll have to maybe convert grams to moles, but calculating molarities from moles and volume maybe by using mass first. Be able to use the molarity equation to solve problems, and then be able to do dilution problems using MIVI equals MF.